Hello Module 14 fans. In this video, we're going to be covering pages 502 to 505, which is chock full of examples and on your own 14.3 and 14.4. So, as you remember from the last video, we're going to be looking in more detail at the rate equation, which is R is equal to K, which is a constant that's unique for each chemical reaction. And the constant is multiplied by the concentration of the first reactant to a certain exponent times the concentration of another reactant times to the power of that particular exponent. And so we're going to start off with example 14.3, which covers pages 502 to 504. So in this reaction, we have nitrogen monoxide combining with chlorine gas. And so our two reactants then that go into this equation are the nitrogen monoxide, that's our A, and our B is the chlorine gas. And they combine to form this nitrosyl chloride. And in order for us to determine the rate equation, we need to work with this formula and determine first the two exponents of these by analyzing the data here, and then we'll be solving for K and then plugging them back into the equation. So for our first one, we'll be finding X. So here is just a review of exactly what the equation was that we're working with. And you can see here we've plugged in the two reactants into our rate equation formula. Now first solving for X, X is the exponent that's correlated to the concentration of the nitrogen monoxide. And in order for us to do this, we need to compare the data between trial 1 and trial 2, because between these two trials, the NO is doubled, but the chlorine gas stays the same. So we're comparing this column with the doubling of the nitrogen monoxide to the rate. And the rate is the rate increase is determined by dividing the 0.076 by the 0.019, and we find out that the rate quadruples, whereas the nitrogen monoxide is doubled. And so since it increases from a 2-fold to a 4-fold, the question is asked, to what power do we raise 2 to get 4? So in other words, the answer would be 2 squared, or 2 to the second power is 4. So X equals 2 because of this 2 here. So now we're going to determine Y. So we determined, as I said before, X is going to be 2, but now we have to determine Y. Y is the exponent for the concentration of the chlorine gas. And in this case, we're comparing data between trial 2 and 3 because the chlorine gas is doubled, but the NO stays the same. So we're looking at this column, which is doubled, and comparing it to the rate, which is also doubled. And since they're both doubled, it's considered a 1-to-1 ratio, and so Y here is equal to 1. And when you have a 1 there, they don't actually write the number 1 in, it's just understood that it's a 1. So, now we know X is equal to 2, Y is equal to 1. We can put those into the formula. The R is equal to K times the NO to the second power, the Cl2 to the first power. And then we can take data from trial 1, we'll go back to that. This row here, right, we have 0.5 molar, 0.5 molar, 0.019 moles per second. and we're plugging in those values here. Here's the rate change, the two concentrations, and we have K as the only variable. So we can rearrange and solve for K. And so here we have an interesting unit for K that emerges. It's 1 over the mole squared times seconds. The book points out that the units for the rate constant will vary because they depend on the exponents, right, of the rate equation. Then once we have our K, which is here, we can plug it into the final version of the rate equation. So we have R equals this K that we solve for times the NO to the second power times the Cl2 to the first power. All right, let's look at our second problem on this example. Here we have C4H9Br, that's one of our reactants. It could be known as 1-bromobutane or 2-bromobutane or tertiary butyl bromide. Also the product that's yielded is the C4H9OH, which is known as butanol. Because these are such tongue twisters, it reminded me of that Dr. Seuss book. And when Tweedle Beetles battle with paddles in a puddle, they call it a Tweedle Beetle puddle paddle battle. All right, so in order to determine the rate equation for the following reaction, and so we have the reaction here, we have the data from the rate study, and not surprisingly we're asked what is the rate equation for this reaction. So we know first of all that this is going to be our A for the rate equation and this is our B. So those have been substituted in here. And so we have K as our constant and the X and Y. So our first step is going to be to solve each for the X and the Y by analyzing the data in this chart. So finding X, right? This was our initial equation. This is the value, the molecules, so to speak, the reactants molecules plugged in for the A and the B. And then we're going to know that X is the exponent for the concentration of the C4H9Br. And we will compare data between trial 1 and 2, because in this case, that reactant is doubled, but the OH minus, the hydroxyl ion, stays the same. So we're comparing this column to this column here. This is doubled and this is doubled, which gives us a 1-to-1 ratio. So the X is equal to 1. So this X up here would be equal to 1. And then as I mentioned, when it's 1, you don't write the 1 in. Okay, so spoiler alert, sometimes you can get a 0 exponent. Sometimes the rate of a chemical reaction will be unaffected by the concentration of one of its reactants. In this case, the exponent of the rate equation is 0. So let's see perhaps an example of that. So looking back at this equation that we've been working for, now we need to solve for Y. So Y is the exponent for the concentration of these hydroxy ions. And in this case, we're comparing data between trial 1 and 3, because here the hydroxy ions are doubled, but the C4H9Br stays the same. So we're comparing this column to this one, because, and we see here that the rate stays the same. In other words, the reaction rate is not affected by the concentration of these hydroxy ions. So in this case, our Y is equal to 0. This is important. This Y would be 0. And since anything to the 0 power always equals 1, we drop this term from the rate equation, that OH there. So let's look at this in some more detail. We know X equals 1, Y equals 0. We have the R, and we have the reactants concentrations, the 1 and the 0. We're going to drop this one because it's just equal to 1. And then now we can solve by K for using data from trial 1. Could have been trial 2 or 3. You should get the same answer. However, in the book, they particularly use trial 1. So if you looked back at the chart, here we're looking along this column here. All right, we have the rate that's determined there, 0.001 moles per second equals K times 0.1 molar. And then you solve for K. You get this unique unit, right, 1 over per second. And then you would take this value for K and plug it back into your equation for R that was listed up here. And then this is your final answer for the rate equation. Okay, now let's look at on your own 14.3 on page 505. Here we have this reaction, hydrogen gas plus the nitrogen monoxide equals N2O plus H2O. And this is the data we're working at these various trials. And we'd like to know what is the rate equation for this reaction. So in this case, our A is going to be the hydrogen gas, and the B is going to be the nitrogen monoxide. So we can fill those right in here in the rate equation. Now our next step is to find our X and our Y. So finding X, right, this was our rate equation with the two reactants plugged in. X is the exponent for the concentration of H2. We'll compare the data between trial 2 and 3 because here the H is doubled but the NO stays the same. And then we see in this case the rate is doubled. So since the H2 is doubled and the rate is doubled, it's a 1-to-1 ratio. So X, this X here would be 1. Now finding Y. Y is the exponent for the concentration of the NO. We compared data between trial 1 and 2 because here the NO is doubled, but the hydrogen gas stays the same. So our rate is jumping from this number to this number. If you divide them, you find that the rate quadruples. It's 4 times as much in trial 2 as trial 1. So since it increases 2 to 4, we ask, to what power do we raise 2 to get to 4? And since the answer is 2 squared is 4, so our Y is equal to 2. And that's up here. This NO would be up to the second power. Okay, so we know X is equal to 1 and Y is equal to 2. And so we can write our rate equation K of the hydrogen gas. There's like an imaginary 1 there, the nitrogen monoxide to the 2. Then we can put in data from one of the trials. It could have been any of the ones, but in this particular case, we're using these numbers. Back from the table, that's back here, we're using one of these trials, trial 1 probably. Those are plugged in. Then you solve for K. Again, you can have some unusual units, 1 over moles squared times seconds. And then you take this K and substitute it, this numerical value for K, you substitute it in for the variable here, and then just follow with the same equation at the end. All right, so now let's look at our last on your own in this sequence. It says ozone can be destroyed by certain pollutants, one being the nitrogen dioxide that is expelled from the exhaust of cars and planes, the reaction that governs this process is this, the NO2 plus O3, you get NO3 plus O2. And here is the data from our trials. What is the rate equation? So we'll follow the same procedure. First, we'll write the initial stages of the rate equation with this is our A and this is our B. So we have it here. The R equals the K. This is our A squared, or not A to the X and B to the Y. And we'll start off by finding X. We're going to compare the data here between trial 2 and 3, because in this case we're looking for the NO2. The NO2 is doubled, but the O3 stays the same. So we're comparing this column to this column here. So this is doubled and this is doubled, which means it's a 1-to-1 ratio. So X equals 1, and that X here would be equal to 1. Now we're going to find Y. Y is the exponent for the concentration of the O3. We'll compare data between trial 1 and 3 because this O3 is doubled, but the NO2 stays the same. Now in this case, our rate is also constant, it doesn't change. And when that happens, when the rate is not affected by the concentration of the reactant, then we say that Y, or that exponent, would be equal to 0. So this Y here is equal to 0. Okay, so since our Y equal to 0, we dropped that O3 and the brackets around that from the equation. We have R equals our rate constant times the concentration of the NO2. Since X was equal to 1 here, we don't write the 1, it's just understood it is. Now we have to solve for K by plugging in data from off the initial chart that we were working in. So again, we have this trial 1, right? You can see this is the concentration of the NO2, and this is the instantaneous reaction rate. So we plugged those numbers in here. Then you rearrange and solve for K, and you get 8.8 times 10 to the second, 1 over S. I know in your book it says 880. It's the same thing. And then you just take this numerical value that you solve for here and plug it in for K for your rate equation. All right, so that's it for that video, and we will proceed on in the next one.